Today we're going to talk about our maximum cell potential, so we can directly relate this to our free energy between the reactants and the products within the cell. So our equation is, that is not a negative sign, that's just like a bullet.
Oh.
Let's make that a bullet. Woo. Make it something. So it is negative, or not negative, oh my gosh, delta G, so our Gibbs free energy, which is in joules, is equal to our negative N being our moles of electrons. So you know how we come back and we have to, if one has 5 electrons and the other side has 2 electrons, and we multiply everything to get to 10. So that would be 10 electrons, 10 moles of electrons. F is Faraday constant, and the Faraday constant is, we'll just use 96,500, and that is coulombs per moles of electrons. And then we have E, which is our cell potential, which we have been determining for the last couple of days. And cell potential is in volts. But we also know that a volt is a joule per coulomb. And that's how we get delta G to equal joules. Okay, so if we have our cell potential has to be what to be spontaneous?
Positive, right?
Positive. So a positive E is going to give me what when we plug that in here? What's it going to do to my G? It'll give me a negative, and if we have a negative G, then that means it is spontaneous. Okay?
Is that why it was positive 2 on this?
Is that why G?
Mm-hmm. Any questions there?
I forgot how to spell something. Sorry. S-P-O-N-T-A?
A.
Yeah.
And E-O-U-S maybe?
Okay. Sorry.
All right, so let's go ahead and go do some problems.
Oh.
So the very first thing we need to do is, if you look here, it says calculate the standard free energy. So that means we're going to do delta G. And we're looking at, here we can see that this is a redox problem. So we know delta G is equal to negative NFE. This is on your reference chart too, so if you forget it. And then it says to calculate equilibrium constant. So what equation do we need to calculate the equilibrium constant? Negative Ratlink. Some of you guys forgot that it was negative Ratlink. So delta G is equal to negative RT ln. Okay. No, we're not going to do that. Okay, so first of all, very first thing we need to do is split up our reaction. So Mg goes to Mg2 plus 2 electrons. Pb2 plus 2 electrons goes to Pb. And they are the equal moles of electrons, so I'm just going to go ahead and balance this out. Or rewrite the equation. What do we get for Mg? 2.37. And for the other one, we get negative 0.13. Yeah. So 2.37 volts, and we have 0.13 volts, negative 0.13 volts. So we end up with 2.24 volts. And that is our E naught. Now we're ready to go and find delta G. So delta G is equal to negative NFE naught. Negative, what's our number of moles of electrons? 2 moles of electrons. Oh, that should be PB right there.
Oh, that's what I was gonna. Yeah,
I saw you guys look at that and I was like, oh.
Is this constant that we're using on the tape?
The Faraday constant? Yes.
It's on the.
So 2 moles, our Faraday constant is 96,500. And our E naught was 2.24 volts.
Ms. White,
Yes.
I know you briefly explained how you calculated the volts like in the previous slide, but please do that again, because
Since this is a 2 and this is a 2,
so it's off of the electrons.
so it's off of the electrons.
So, and then if it had been like a 4 to 5, you'd have
Then
to
we
give
would
them
be
the
the
same
common
number.
multiple.
You want scientific notation or just normal?
Normal's fine.
Okay. Negative 192,998 joules. I mean,
No, try it again.
Negative 432,000.
oh, I did plus for some reason.
Negative 432,000 and what?
320.
So I'm going to do 300. This is joules.
I think I accidentally put.
Why are we doing 300?
Did you say 320?
Mm-hmm.
I was just doing sig figs.
Wait, so whenever we use
Where do we get the
equation,
first thing? Like which number we from?
I was just kind of just rounding it.
Okay, I'm just. Okay.
I was just rounding it.
sig figs not gonna matter really much to this one.
Mm-mm. I'm not really caring about sig figs right here. This is per mole of reaction. So now that we know that, now we can go and we can find delta G. We can find L and K. So negative rat link. Delta G is negative 432,300 minus R, or equal to negative R, which is 8.31, times T, which is 298 because it says it's standard, and L and K. So L and K is equal to, I got about 175. And if we take E to that, then K is a very huge number. And what is that?
6.57 times 10 to the positive
6.58 times 10 to the 75th.
I got one.
That's what I got.
Dang it.
What-
No, if you
76.
round, then you get a different number, but if you didn't round, then you get the 6.571.
So the not rounding is with the 43232.
The not rounding is the 6.576
Right,
times.
but that's using the.
And then, but if you just use the 175, then you get the 1.00.
Oh. Got you.
So it's 1.00
Yeah.
if we rounded that. Since I have it on here as rounded, let's do that. So it's 1 point
00 times 10 to the 76.
times 10 to the 76. Okay. It's such a huge number that it's not going to make very much difference anyways.
The decimal one's funny.
Okay. Any questions on that? All right. So that is part of your homework for tonight. The next part is we're going to look at concentration cells. And a concentration cell, what happens is this is not at 1 molar. Okay, so if you see here, we're not in standard conditions anymore. So we have to look and see what's going to happen to our cell potential if we start decreasing or increasing our molarities. Is our cell potential going to go down, or is our cell potential going to go up? Okay. So let's do this. This is the Nernst equation. This is what we're going to use to equivalate or go back to get our new E of our cell when it's out of standard conditions. The Nernst equation is not on the AP, but therefore it is not on your reference chart. This is not on your reference chart. But you can use this to answer questions, to make it easier to answer questions if you have the Nernst equation. So my advice is, prior to the AP exam, is programming it into your calculator. Because they don't erase your calculator. They just don't. So that you can have programs and everything in there. So just remember, I'll remind you to put that in there because it should be able to help you out. So E cell, so when we're not in standard conditions, is equal to our E naught, which is standard conditions, minus 0.0529 divided by N, which is our number of moles in the balanced reaction, log of Q. And Q, remember, is our products to whatever power over the concentration of our reactants to its coefficient power. This is the old equation, but after substituting everything in, it reduces down to what I have here. So this is what we're going to use on the day of the test. In here, if your test should have Nernst equation on it, then I am going to put it on the board for you. We're going to cross this out because we're going to come back to that here in a minute.
We're going to come back to it?
Yeah, well, not to it. It's on another slide, so I can work more.
So we're not coming to this particular slide again?
No.
So I can fix that permanently.
Michael Ann's always...
Well, you say cross it out, and we're going to come back.
Sometimes you just go, oh, cross that out.
I'm like, oh, let's go back. Sorry. And y'all are like, oh my gosh. Okay. So one thing I want to talk about before we go do some problems is the following. It says explain the difference between E and E naught. E naught is standard conditions. So I'm putting STD conditions. And those are 1 molar or 1 atmosphere at, which equals at 25 degrees Celsius.
Now, does it have to be all three of those to be standard?
Yes. Anything shifts out of that, then it's non-standard. Now, E without the E naught is any condition. When is E equal to 0? So E is equal to 0 when a cell is in equilibrium. When is a cell in equilibrium? When it's dead.
You know, I keep feeling like you're talking about like biology cells and you're not. And then you make something, you say
Cell
something.
is in battery cell, right?
Yeah.
So would this be a full, like an entire battery cell, like a AA?
Yeah.
Okay.
You're talking about just any, yeah. And then when is E naught equal to 0? E naught is equal to 0 when you have a concentration cell. So that's when we've moved out of those standard conditions.
I always think of equilibrium as being like calm, but if you have a dead battery, that's like the opposite of what you're doing.
Yeah. Well, you think about if you have a dead battery equilibrium, if it's at equilibrium, we're not pushing anything back and forth anymore. We're not going to get any voltage out of that.
So as soon as you start to charge it, it will be equal.
Mm-hmm.
Does the battery have to be negatively charged to have power? You couldn't be positively charged and have power.
Battery has to be positively charged.
Okay.
Now,
We're adding electrons to make getting
we're
getting closer to equilibrium. Right? The dead battery is no charge. So in all the equations, I'm confusing myself. It's okay.
okay. Let's go do this problem. The one I set the mark out. Now it's bigger, so I can have room to work. Calculate E naught. So we're just doing our standard E for this reaction. So the very first thing we need to do is what? Half reaction. So zinc becomes zinc 2 plus 2 electrons. And we have 2 electrons plus copper 2 plus to give me copper. Huh?
These are the simple.
I always have everything worked out prior to class. So now let's go find our volts. 0.76, and for copper is 0.34. We should know copper by heart by now. So this is 1.10 volts is our E naught.
Wait, you're not going to subtract?
We have to add them.
Because
They're both positive because if you look on the chart and you use the chart the way it is, then you subtract it but we flip and add. Does that make sense? If you're looking at the chart, it says 0.76 and negative 0.34. So if we subtract that, then we're still adding. It just depends on what you want to do. Okay, so the next thing says now we have we've kicked it out of equilibrium, or we've kicked it out of standard conditions. And so we want to know what is our new cell potential. So cell potential, we're going to go to the Nernst equation. E cell is equal to E naught minus 0.059 over N, our number of moles, log Q.
You said E cell is equal to E naught?
Is equal, yeah.
And this is just continuing what we had
Yes. So E naught, what we just found was 110 volts. Or, sorry, 1.1 volts. Minus 0.059. What's our number of moles of electrons? 2. And then we have the log of our products, which is 0.0001 to the first power over 1.0 to the first power.
let's go.
Okay, so first thing I want to talk about before we go and answer this. If you have a log and it's greater than 1, what is your answer going to be?
Log greater than?
If you have a log and you're taking the log of something greater than 1, what's positive? If you have a log and it's less than 1, then it is negative. Okay, so let's do a prediction here. If we take 0.001 divided by 1 and take the log of that, is that going to be a positive number or is it going to be greater than 1 or less than 1? It's going to be less than 1. So if we have a number that's less than 1 and we're subtracting it, it's less than 1, which means it's going to be a negative. And if we're subtracting a negative, then what's our E cell going to do? Our E cell is going to go up. So we're predicting that our E cell should go increase.
Is it going to be by a lot or by a lot?
It just depends. Probably by a little. If we have a positive number and we subtract a positive number, then that means our E cell would go down, which will decrease our potential. All right, so what did you get for that? 1.2, I'm going to go say 22 volts. And that is our E cell. So it went up, which is great. So now let me put this in a different perspective. If I take my equation, and I tell you, you have 1 molar of copper, 2+, and you have 0.0001 molar of zinc, 2+. Predict to me what is going to happen. Which way are we going to shift? We're going to shift to the right. We've decreased the zinc, right? So we've shifted to the right. So if we shift it to the right, we are going to increase our voltage, increase the cell potential. So increasing the cell potential by decreasing our concentration of the zinc. Any questions? One more problem and we're done.
Why did they choose E to represent cell potential?
All right, so this next one, this one we had it put together. We knew which way to put it together. Now we've got to decide which way we're going to put together the next cell. So we have 2 cells here, or a cell, and it's made of silver and cadmium. So go and find silver and cadmium on your chart.
Silver's 0.8.
Silver's 0.8. Cadmium is negative 0.4.
Yeah.
So that means it's going to be flipped to be positive. So silver is written just like it is on the chart. And that is 0.8. Cadmium is flipped. And that is 0.4. And we add those together and we get 1.2 volts is our standard E0.
Why did you flip AG?
AG is not flipped.
It's cadmium, it's a smaller number.
If you go to your chart, AG is 0.8 and CD is 0.4, negative 0.4.
Okay, and so we don't write it the way that it's given to us with the slash?
No, you're having to figure it out, how to write it.
Because I was thinking something that write to the OR because we do this slash.
No, this one, you have to figure out how to write it because we have to make the cell so that it does give us a positive cell potential. So if you wrote it the way it is, you'd get a negative cell potential. Okay?
So we only use our chart to make these two.
Yes, you use your chart when you need to make your cell, unless if it's already given you the equation, you know how everything needs to be running. All right, so the next thing I want to do is go back and let's balance this out. So we need to multiply silver, everything by 2. So that gives me 2Ag plus CD yields 2Ag plus CD2 plus. And now we go and we do the Nernst equation. E cell is equal to E naught, which was 1.20 volts, minus 0.059 over, what's our number of electrons? 2 times the log of the concentration of our product, which is our CD plus. So that is 1.5 to the first power over our 0.2 to the second power.
How do we determine which one goes to product?
Huh? Well, these are solids, so these aren't going to be, this is what we have to determine. Once you've written the equation, you can see what your product is.
Is it usually going to be the one with the charge? That's going to be the product that you look at for products over reactants?
Yes, products over reactants going to always be, because those other ones are solids. Remember, we don't put solids in equilibrium equations. So what do we get? What are we predicting this log is going to be? Greater than 1 or less than 1? Greater than 1. So we're predicting that we're going to have increase or a decrease in our cell potential. So if we put this in there,
$1.15.
1.15 volts. Okay, so now go up to our equation. I'm going to put in that we have a 0.2 molar silver solution and we have a 1.5 molar cadmium solution. So looking at that and knowing Le Chatelier and which way we push and pull, which way is this going to go? It's going to go to the left. And when it moves to the left, what's it going to do to our potential? Decrease. So we decrease the driving force by decreasing our silver concentration and increasing our zinc concentration. Therefore, your voltage, cadmium, sorry, yes. Therefore, voltage decreases. Okay? Any questions on that? So you can do it mathematically, you can do by, if it wants a number or if it just wants to know what's going to happen, you can use your Le Chatelier and try to figure out what's going to happen by doing that. So homework is C tonight.